Hi dear friends, myself Bhausab Sonone, Assistant Professor, Department of Chemistry, Gokhale Education Society, Arts, Commerce and Science College, Jawar, District Palghar. Dear friends, in the previous lecture, we discussed about the detection and the measurement of radioactivity. In that lecture, we also discussed that the nuclear radiation shows different types of emission like alpha, beta and the gamma, and these radiations are able to produce the ion pairs when passed through inert gases, and these ion pairs when migrate towards the electrodes of opposite charge get discharged and reported in the form of current as a count, and magnitude of this current can be used to find out the type of ionization, whether this ionization is because of alpha particle, beta particle or the gamma particle. And in order to detect and the count of this type of ionization, various instruments are used, and in the previous lecture we discussed about the first type of the instrument called as Gieger-Counter. Dear friends, in the previous lecture we also discussed about the principle and the setup of the Gieger-Counter, how it works in order to count and in order to detect the radiations emitted by any radioactive element, and what is the setup of the Gieger-Counter. So in the previous lecture that we discussed that when ionization chamber has a potential between the two electrode, one is the cathode and another one is the anode, but copper cylinder acts as the cathode. This copper cylinder acts as the cathode, and the central wire, tungsten wire, acts as the anode in the range of 900 to 1400 volts whenever applied. The internal amplification is take place in the order of 10 raised to 8, and the number of ion pairs produced is independent of primary ionization. So it was the principle of this, and this is the experimental setup. So this is experimental setup. I have taken this image from the Google. So this is the experimental setup in which one copper cylinder is there. The wall of this copper cylinder acts as the cathode, so it carries the negative charge, while the central wire called as the tungsten wire, it is present at the center of this copper tube and it acts as the anode. It means it carries positive charge. What happens, dear friends, this copper cylinder or this tube which is made up of the copper, it also contains a mixture of 90% argon and the 10% of alcohol or the bromine vapor, which is present inside this tube. Again, the one end of this tube is having window called as the mica window, which does not allow the escape of these argon atoms or the molecules out of this tube, but it allows the entry of this ionization radiation into this tube. So this is the characteristic of this mica window that we all discussed in the previous lecture, and this is the readout device which is used to count the magnitude of current. So dear friends, today in this lecture we are going to discuss about the actual working of this Gieger-Counter, how it works. So this is the construction that we discussed in the previous lecture. So during the discussion of working of this Gieger-Counter, these ionizing radiations, particularly alpha and the beta radiations, why not the gamma radiations of the gamma particle that we will discuss later on, but these ionizing radiations which are only the alpha and beta particles, whenever enter the mica window, these are responsible for the ionization of argon atoms, and there is a formation of ion pairs, because this whole working or the working of this whole Gieger-Counter is based upon the formation of ion pairs. So whenever, already I told you, whenever the ion pairs are formed, so one species will carry positive charge, another species will carry negative charge, but these alpha and the beta particles are responsible for the ionization of which particles or ionization of which atom? these are responsible for the ionization of argon atoms which are already present in the tube of copper cylinder, and these are responsible for the formation of electron. We can say that these are the electrons in the first ionization. So these are the primary electron, because later on you will come to that these electrons are responsible for the secondary ionization. So these are the primary electrons which are formed because of the ionizing radiations alpha and the beta whenever they will enter into the tube through mica window. So this is the ionizing radiations, for example either alpha or the beta radiation. So whenever these radiations will come inside this tube, so these are the argon atom. These ionizing radiations are responsible for the ionization of this argon atom, and there is a formation of electrons, or there is a formation of ion pairs. After this, what happens? The water electrons which are released here, these electrons are accelerated towards the oppositely charged, means the positive electron, and which is anode, that is present in the form of tungsten wire at the central part of the tube, and that's why these electrons released due to the ionization of argon atom due to alpha and the beta particle, these electrons will accelerate or will migrate towards the central tungsten wire which acts as the anode. So this is okay. So this is the tungsten wire which acts as the anode. So these electrons which are released here, these electrons will move towards this tungsten wire which acts as the anode. Again, the positive ions which are formed during the formation of ion pair, these positive ions of argon atom migrate towards the cathode, means the walls of the cylinder, and there these ions will accept the negative charge from the wall of the container and itself get discharged. So this is very simple, that electrons are moving towards the tungsten wire which acts as the anode, and positive ions will migrate towards the walls of the container or the walls of the tube or the walls of the cylinder which acts as the cathode, means it carries the negative charge, and these ions, positive ions, will accept the negative charge from the copper metal tube and get discharged. So these fast moving electrons reach the anode in very short time, because of these electrons are having very negligible mass, their size is negligible. That's why these electrons are fast moving electrons, and these fast moving electrons will reach anode in a very short period of time, and these high energy particles are again responsible for the more ionization, and that's why these electrons will responsible for the formation of secondary ion pairs. So this is very simple, that whatever these electrons are released here in the first ionization, these electrons will move towards this tungsten wire which is the anode in a very short period of time, but during this process, during this transfer, these electrons are again responsible for the more ionization, and that leads to the formation of secondary ion pairs. So this is very simple, that the electrons whenever moving towards the tungsten wire, then these high energy particles or the high energy electrons are responsible for the second ionization, that we call it as the secondary ion pairs are formed. These secondary electrons which are released again cause further ionization. So this is the next step of ionization, in which the secondary electrons will cause more ionization, and all electrons which are produced get discharged at anode, and that discharge of all electrons will register in the form of current. So this is very simple, that so this all electrons after primary, secondary or tertiary ionization, all electrons get discharged around at this anode, and the discharge of this all electrons will register, or it will counted in the form of current. So this is the simple case, that secondary electrons cause further ionization, and all electrons, the whatever electrons due to primary, secondary or tertiary ionization, all these electrons get discharged at anode, and that discharge of electrons at anode is resistor is recorded in the form of current. This current is again amplified and registered as a count, and count per minute for a given source. So whatever current is amplified, after amplification of the current, it is registered as a count, or in the form of count, or in the form of count per minute in the presence of a given source. In the presence of a given source, it means that whenever we are going to study this, we are going to study the ionization due to this alpha and the beta particle, but this alpha and beta particles are emitted by means of some radioactive element or the radioactive source, and this whole process is carried out in presence of a radioactive element which is placed here, and definitely these alpha and the beta particles are emitted by the radioactive element or the radioactive source, and that's why this count per minute which is recorded in presence of an radioactive source or the radioactive element is called as the experimental count. So this current is amplified and registered in the form of count per minute in presence of a given source, and that's why this count is called as the experimental count, which is recorded with the help of some digital display of the GM counter. What happens in the next time? The same process, whole process is repeated again, but during this repetition, the radioactive element source is removed. Means the whole process is repeated in absence of radioactive element, and the water count due to any factor, due to any reason, that count is called as the background count. Actually, the water count will be there, that will be because of the current, because of the ionization, but because this ionization is not because of the alpha and the beta radiations emitted by the radioactive element, but this ionization will be because of some cosmic rays. It may be because of minute quantities of some radioactive gases which are already present in the copper cylinder or the copper tube, like radon and the thoron in the atmosphere, which are already present in the atmosphere, and the whatever count of the current which is recorded in absence of an source of radioactive element, that count will be called as the background count. It is just like a titration. In the titration we are doing the two titrations. One is called as the blank titration in absence of sample, and another one is called as the back titration in presence of a sample, and the difference of these two titrations or the titrating reading will give you the actual concentration of the sample or the actual amount of the sample. In the same thing, whenever we will count, we will record the count per minute in presence of an radioactive element, then that count will be called as the experiment count or the experimental count. And whenever the count per minute is recorded in absence of radioactive element or the radioactive source, it will be called as the background count. Definitely it will have some, it may or may not having some value, but that will depend upon the conditions. But this background count, it is in absence of an radioactive element, and that's why the actual count can be calculated by taking the difference of these two, experimental count minus background count. So this value will be smaller as compared to experimental count, because in the experimental count there is a contribution of both, definitely radioactive element and if there is a presence of some another radio element present in the atmosphere, that both will contribute in the experimental count. But in the background count there is no contribution of the radioactive sample or the radioactive element. There is a contribution of only radio element which are present in the form of some cosmic rays or the any minute quantities of radio element already present in the atmosphere. But the actual count from these two can be calculated by taking the difference of these two, experimental count and the background count. So actual count which is obtained here, it gives the number of particles emitted by means of an radioactive element or the radioactive sample, and that actual count will be helpful because in the start of this presentation we have seen that how many count is given by, or the how many ion pairs are given by alpha particles and how many ion pairs given by means of a beta particle. Definitely both are having the different value. So from this actual count we will be able to get the number of particles emitted by the radio element, What happens during this process whenever the ion pairs are formed? Definitely already I told you these electrons are moving towards the tungsten wire, while this positive ion moving towards the wall of this copper cylinder or wall of this metal tube. But whenever you will consider the transfer of this or the movement of this electron and the positive ion, these electrons are having very negligible mass and they move towards this tungsten wire or they move very fast. But whenever you will consider the speed of this positive ion which are moving towards the cathode, means which are moving towards the wall of this tube, the speed of positive ion is very slow as compared to the speed of electrons. So electrons are moving fastly towards the tungsten wire, and these positive ions moving towards the cathode is very slowly, or these positive ions moving very slowly towards the wall of the container which acts as the cathode. So these heavy positive ions move towards the cathode at a very slow rate and forms one layer around the anode or in the vicinity of anode. Because of the slow speed of the positive ion, there is a formation of one layer, or there is a formation of some sheet of the positive ions in the vicinity of anode. And due to the formation of this layer, due to the formation of this sheet of positive ions which are moving towards the cathode, and these are having very slow speed as compared to the electrons, this field strength get reduced and this counter becomes ineffective, means it is not capable to record the next pulse of current or the next pulse of the count. So this field strength of the counter get reduced and counter becomes ineffective and the second pulse cannot be recorded. This is the problem here. And the time during which the counter is not able to responding to a second event of ionization, that much time is called as the dead time. So definitely this is the time period in which the counter is ineffective, counter is not working. Definitely there with the continuous event of ionization, but some events of ionization will be missed by the counter as it is become ineffective, incapable of responding a particular ionization, or it becomes ineffective. That's why it misses some events of ionization. The time at which or during which the counter is not able to respond to the event of ionization, that much period is called as a dead time of the GM counter. After some time again, the layer of this positive ion or the sheet of this positive ion move towards the cathode, and counter again becomes active. That we call it as the counter becomes, or counter is able to resume counting on next pulse of or the next event of ionization, and that's why the counter will be able to record the next pulse of the current. So during this what happens, definitely this is very important time in which it will miss some event of ionization, but after some time it will become active and it will start to record the second pulse. At the same time, already I told you there is some mixture present in the tube. One is the argon atom, another one is nothing but the ethyl alcohol or the bromine vapor. Already we got the function of argon atom. Argon atom are responsible for the formation of ion pairs, and these ion pairs will helpful for us to find out the type of particles emitted by the radio element. At the same time, the 10% ethyl alcohol or the bromine vapors which are present in the tube, their function is to prevent the second avalanche. What is second avalanche? That is very important. It is generated due to the photoelectrons. Photoelectrons, these are the low energy particles. So these generated due to photoelectrons emitted by the action of photons on the walls of the tube. These photoelectrons are responsible for the more ionization. But what happens? These photons which are emitted when positive ions and electrons combine, these photons are emitted. These photons when positive ions and electron get combined, these photons are emitted. But what happens actually, the water molecules of alcohol and the bromine that will combine with these low energy electrons, and as these low energy electrons will combine with the molecules of ethyl alcohol or the vapor, definitely these low energy electrons will not be responsible for the further ionization, and hence it prevents the generation of second avalanche. So these are nothing but the low energy particles, low energy electrons, which are not actually responsible for the uh, which are not actually available for the further ionization, as this combine with the molecules of alcohol or the bromine which is present in the copper tube, and that's why this is the particular function. So this ethyl alcohol and the bromine vapor, these are responsible to prevent the second avalanche, because this molecule combine with the that is with low energy electrons which are formed because of the photons. So there are some limitations of this GM counter, or to use the GM counter. The first limitation or disadvantage is that voltage used for counting alpha and the beta particle are quite different. So definitely whenever you are going to study a particular sample of the radio element, definitely you have to apply different voltage for the alpha radiations and the beta radiation, or the alpha particle or the beta particle. It means that if you don't know what type of the particles are emitted by the alpha, what type of the particles are emitted by a particular radio element, then it is very difficult to find out the what type, or it is very difficult to identify that type of emission. So in that condition, what voltage should be applied, so that will depend upon the type of particles emitted by the radio element. And already I told you, so once if you don't know the type of emission, then it will be difficult for us to apply the particular voltage, whether we will be not able to apply a particular voltage, because we have to apply different voltage for the alpha and the beta. And if we don't know the type of emission, then definitely it is unknown part for us to application of the voltage. Again, gamma radiations or gamma particles cannot be measured by this type of the counter, GM counter, because gamma radiations are not able to, or these are gamma radiations are not able to ionization. So as because the low ionization power, or very low ionization power of gamma radiations or the gamma particles, we are not able to detect, we are not able to find out the type of this type of the we are not able to measure this type of the radiations of the particles whenever emitted by the radio element, as these are not able to ionization of that is radon in the argon in this counter. Another one means, by using this counter, by using GM counter, only those radiation or those particles can be detected or measured which are responsible for the ionization. So the radiation must have strong ionization power, then the radiations of the particles can be detected with the GM counter, and that's why gamma radiations are not able to cause the ionization. That's why this cannot be detected or measured with the help of GM counter. Another one, already we discussed about this. If any particle enters the cylinder in a time in which the counter is not active, counter is ineffective, then that particle will not be counted, that particle will not be measured by the GM counter, and that much time, or during the time in which it is not recorded, that time, that period is called as the date time of the GM counter. So any particle if enters during the date time of GM counter, then that event, that particle cannot be detected and it cannot be measured. It means it cannot be counted by this GM counter during its date time, or during its period of date time. So these are the some limitations of the GM counter. Definitely, in order to overcome these limitations, we are having another device, we are having another counter which will be helpful to overcome these limitations of the GM counter. And definitely that is the second counter that we are going to discuss in the next part of this video, that is called as scintillation counter. So friends, we will resume again to discuss the second counter, which is used to measure the particles emitted by any radio element, called as scintillation counter. Thank you friends.